Ladies and gentlemen, welcome to the second webinar of our summer series, Master Connections, with today's topic about moment connections. My name is Vlastivil. I work as a technical channel manager at IDEA StatiCa Asia and Pacific, so I'm based in Singapore. We're running on a GoToWebinar platform. It means that you are all muted by default. However, feel free to ask any question, but please use the question panel that is in the GoToWebinar application. All unanswered questions will be then answered after the webinar. And just to remind you, the whole session is being recorded, so we will then upload it to corresponding channels. So let's have a look at today's topics. So the topic is moment connections. At first, we will define what is a moment connection and how to properly classify the connection based on its stiffness. Then I'll explain how the stiffness analysis in IDEA StatiCa Connection works. Then I'll show you a practical demonstration of a connection that is designed and then analyzed in the connection application. And last but not least, we'll go through the results of the stiffness analysis. So I'll explain how to properly read the results. So what is a moment connection? You can see an image in this slide. Moment connection is a type of a steel joint that transfers bending moment from the connected member to the supporting member without any internal forces redistribution, i.e., the connection is rigid enough to transfer the whole portion of bending moment without redistributing the forces to other parts of the steel structure. So moment connections, when we're talking about moment connections, we usually talk about rigid connections. How to classify the connection? Each steel connection can be classified or divided into three classes. The first one is pinned, second one is semi-rigid, and the third one is rigid. That's where moment connections should belong to. Yeah. And the classification of a connection based on its stiffness is code dependent. Each code has its own requirements. So in this slide, you can see a diagram where you can see a classification of connections based on Eurocode. Almost the same would be according to other codes. So for example, AISC and other various codes. And as I said, each code has its own requirements. And usually the requirements are governing on the initial stiffness of the connection, modulus of elasticity, moment of inertia, and theoretical length of the analyzed beam. So based on these values, then the connection is classified as either pinned, semi-rigid, or rigid. So how the stiffness analysis works in IDEA StatiCa Connection? The first important thing to remember is that only one member can be loaded and analyzed when running the stiffness analysis in the connection application. The member can be loaded by 6 components of internal forces. It means normal force, shear forces in both directions, bending moments My and Z, and torsional moment Mx. The initial load input is then used for the evaluation of the alpha factor. So what the software does, it automatically calculates the resistance of the connection and then use also the initial input of loads to calculate the alpha factor. And then it uses this alpha factor to multiply the initial load set. It takes the resultant value and divide these applied loads into 12 individual steps. The load is then applied by these in these steps, and once the connection reaches or it's near its resistance, then those steps are refined, applied again, and of course the analysis is finished when one of the conditions is fulfilled. So this was a brief introduction to the theory behind the stiffness analysis in the connection application and the classification of connection stiffness in general. And now let's have a look at how the connection can be checked, designed, and analyzed in the connection application. So I'll jump off the presentation and start IDEA StatiCa and select the connection application. Now the application is being opened. All right. If you watched the last webinar, getting started, now you know how it looks when you open the connection application for the first time. So there are multiple ways how to create a project in IDEA StatiCa Connection. In this webinar, I'll show you how to use one of the predefined templates. So at first, we'll select the corresponding class. So it will be a beam to column connection. I want to have a beam connected to a continuous column. So in the second column, geometry, I'll select the second option from the left in the first row. And then among moment connections in the third column, in the design column, I'll select the first one in the second row. The last thing I need to do, I need to name my connection if I want to, and then define the initial parameters. So still great, we'll leave it as S355. Bold assembly, again, we'll leave it as M16 8.8 at this point. Weld grade S355. And corresponding design code. So 8 codes in total. I'll be using Eurocode. So I'm done with the initial design setup, sorry, and I can click Create Project. Okay, so now we have the connection as selected in the previous step. At first, I need to change the analysis type. So this time we won't be running the stress strain analysis, the default analysis, but we want to see results for the stiffness analysis. So in the property grid on the right side of the app, I can change the analysis type from stress strain to stiffness. Second step is setting the analyzed member. There is only one connected member to the column, and I want to assess the stiffness of this connected horizontal beam B. So I click on it with a right click and select Set Analyzed. And then it means that this member will be considered in the stiffness analysis later on. I can really see that there is only one input of internal forces on this beam, and those red lids on the column, they represent the supports. So the rest of the connection is supported. Only this member has free end, and that's where the load will be applied. I can also check the load effects. So there is a shear force in the vertical direction, 15 kilonewtons, and bending moment around the y-axis, and the value is 25 kilonewton meters. So what I can do now, I can run the stiffness analysis and see if this connection will be a moment connection or won't be a moment connection. On a first look, because I'm experienced engineer, I have a suspicion that such a connection won't be able to transfer the whole portion of the bending moment. So I would need to probably modify this connection a little bit to make it a moment connection. And again, there are multiple ways how to do it. Either you can use connection library within the application. So after clicking the propose button in the top ribbon, now the software looks for suitable topologies of the connection and shows me all the possible configurations of the connection. So this is one way how you can do it. Also, you can select the filter for moments. So now it shows me only connections that are able to transfer any moment. But I won't be using this. Today, I want to show you how to define and design the connection manually. So I'll do the necessary modifications one by one. Yeah, so at first, we will modify the end plate connecting the beam to the column. So the thickness stays 10 millimeters. I want to have it longer on top and bottom of the beam, and also the dimensions on left and right sides. So now I increase the size of the end plate. I'll also change the value of fillet welds on web of the column, and I'll also change the bolt layout. So I won't be using M16 8.8. After all, I want to change it to M12. So I'll click this plus button on the right side, select M12 8.8 from the library, and now I'll change the layout. So the negative 40 millimeter stays. I'll just type semicolon 65 like this and change the layout on the left side and on the right side accordingly like this. And as a last step, I want to introduce some wideners on the horizontal beam. So I'll select the operations button in the top ribbon and select the wideners from the manufacturing operations like this. So now I need to be really sure that I have it connected correctly, because now I see that there is some clash warning. It means that these wideners are not connected to the end plate, but directly to the column. It means they are going through the end plate, which would be a mistake, right? So I want to set that those wideners are related to the end plate. Now the warning message disappeared, and it looks quite good. What I will do, I'll leave the thickness as 4 millimeters. The parameters of wideness looks good. All I'll do, I'll change again the thickness of the fillet weld on both stiffeners. All right, that's it. I'm quite happy with my design, and now I can run the analysis. Yeah. So I click the calculate button, and now the analysis is automatically performed by the software. So by default, the stress strain analysis also runs in the background. So you will see results, you will see stresses, you will see plastic strain if there is any. And now that's when the application applies the loads for the stiffness analysis divided into those initial 12 steps I was talking about. So it calculated the resistance of the connection. Based on that and based on the initial load input, it calculated the alpha factor and then multiplied the initial load input by this factor and divided the overall values by 12. And now it applies corresponding portions of load in those individual steps. So we're almost there. Okay, we see that the load is above 100%, going down a little bit. So it's near its resistance. So what the software did now, it refined the steps, and now it applies them again as explained at the beginning of the session. So now it basically repeats the same steps, only with refined values. And again, once the connection reaches or fulfills one of the conditions for the calculation to stop, the calculation stops, and we will see the results. Yeah, so again, we're almost there. Even though stiffness analysis is quite complex analysis, you see that it doesn't take that much time to see the results. And now we actually see them. So we see overall results in the graphic scene, overall results in the left top corner. So I'll switch from this design tab to the check tab to see the results. Yeah. And because we have a shear force applied and bending moment applied, we see the results for rotational stiffness. If there is any normal force applied to the model, to the connection, we would also see the results for the axial stiffness analysis. So let's check the results. I select rotational stiffness on the right side of the application, and what I see is a table with results and a stiffness diagram with stiffness curve. And on a first glance, we see that this moment connection, even though it looks like a moment, a rigid connection, it's in reality semi-rigid. Yeah? So this might quite often happen, and that's why it's really important to pay attention to the stiffness analysis to see the results and to really ensure the initial assumption that such a connection is indeed rigid connection. So the blue curve represents the limit for pinned connections. Orange curve represents the limit between semi-rigid and rigid connections. And we see that our stiffness curve is between blue and orange line. It means that it is indeed a semi-rigid connection. And we can see it also on the right side in the table. So what are the options now? Either I can calculate or I can assume that the connection is indeed semi-rigid, but then I would need to go back to my global model and introduce the real stiffness of the connection to the global model. Because if you assume rigid connections in your global FEA model and the connections in reality are only semi-rigid, then this might affect the overall design because the internal forces will be then redistributed differently, and it can really affect the overall safety of your design. So if I decide to continue with semi-rigid connection, I need to go back to my global model, introduce the real stiffness of connections, and recalculate the whole structure again. Or if I want to continue with my initial assumption that I'll work with rigid connections, I need to change the overall stiffness of this connection somehow. So I'll go back to the design tab, and I'll do some modifications of the connection. And the first modification is that I'll increase the thickness of the end plate. And sorry, I forgot to mention that turning on the results of the stress strain analysis can really help with identification of what needs to be changed. So what I see now, I see bigger stresses in both wideners and also the top part of the end plate and of the column itself. So now I probably know that I need to do something with this part of the connection. So now I'll go back to the design tab and increase the thickness from 10 millimeters to 12 millimeters, right? The dimensions stay the same. And actually that's it. And what I will do now, I'll just modify the wideners setup a little bit. So again, I'll increase the thickness of wideners. And again, that's it. So what I did now, I just increased the thickness of the end plate and of wideners. And I rerun the analysis, which I won't do this time because I pre-prepared this connection for you to save some time. So as you can see, it's the same connection, thickness of end plate 12 millimeters, yeah, thickness of widener 6 millimeters, load input is the same. I just reran the analysis and I see again satisfying results for stress strain analysis and also results for stiffness analysis. Now I see in the diagram at the bottom of the app and also in the table on the right side that this connection is rigid. So increasing the thicknesses of wideners and the end plate really helped. So how to read the results? Let's have a look at the table at the top of the right side of the app. So what we see, which item has been checked, what is the portion of load that was applied, right? So we were checking it against the bending moment around y-axis. This is the critical load effect that that was considered during the analysis. This is the initial input of loads, then the bending resistance of the connection, value of initial stiffness, value of secant stiffness, rotational deformation, rotational capacity, theoretical length of the beam, again, very important for the correct stiffness classification, as mentioned at the beginning. And those two values are limit values for classification. So this is a minimum stiffness for a rigid connection, and this is minimum stiffness for a pinned connection. So what I see now is the initial input, 25 kilonewton meters, and the rotational capacity, bending resistance of the connection, 57 kilonewton meters. Yeah. How the initial stiffness is evaluated? Based on the stiffness curve and 2/3 of the bending resistance of the connection. So these 2/3 of bending resistance, it's 38 kilonewton meters. And we know that the initial load input is 25 kilonewton meters. So if I want to know what is the real value of the stiffness, that can be then somehow introduced back to your global model if necessary. In case the value of the bending moment that was set in the application is lower than 2/3 of MJRD, then you know that the real stiffness of the connection is the initial stiffness, SJ_INI. On the other hand, it might happen that the initial load input, the bending moment MED, is above 2/3 of MJRD. In this case, you should either take the initial stiffness and divide it by a corresponding factor that is recommended by the code, or take the value as of the secant stiffness as the stiffness of your connection. So this is how you should read the results of the stiffness analysis. The rest is done automatically by the software. All you need to know is how to properly evaluate the real stiffness of your connection. And of course, after you're done with your design, we're quite satisfied. We have a rigid connection, so we succeeded with our goal for today. We can create a report, switching the tabs from check to report, generating the report containing all necessary information about the connection. You can add it to our documentation and go home because our job for today is done. I'm not going home now because we still have 4 minutes left. So let me jump back to the presentation and introduce you to our own e-learning campus courses that can be found on our webpage and at IDEA StatiCa.com in the support and learning section. We have 3 courses for steel applications, 3 courses for concrete applications. One of the advantages is that those courses are absolutely self-paced, so there is no time limit to finish the courses. And another advantage is that those courses are for free, so everyone can study them. Even people without IDEA StatiCa license, they can either apply for special campus edu license, download the trial version, or create a basic user account. And of course, if you prefer a human touch, you can always request one of the trainings. So again, if you go to ideastatiCa.com, in the support and learning section, there is a section dedicated to training. So you can fill in short form and request a training that will be then provided by your corresponding reseller. What happens after the webinar? Please fill in the short survey. Tell us how you liked the webinar, what could be the next topics for another series of webinars, for example. Also, we will process the recording of the webinar. We will input it into our support center, and we will place it at our YouTube channel. Also, if you're interested in the software, you would like to try the stiffness analysis on your own, don't hesitate to go to ideastatiCa.com and apply for a 14-day free trial version. It is a full version of IDEA StatiCa, so you can explore the possibilities and see the value yourself. And of course, if you would like to have some supporting materials for that, you can go to support and learning section to our support center, where we have plenty of knowledge-based articles, step-by-step thorough tutorials that can help you with the beginnings of modeling in one of the IDEA StatiCa applications, theoretical backgrounds, every possible validation and verification, and many more. So what is next? This series, Mastery of Connections, it doesn't end here. This was just the second part of it. We have 3 more sessions to go. The next session will be held on 8th of August, and the topic will be shear connections. The next one after that will be on 22nd of August, and we'll focus on complex connections. And the last webinar of this series will be on 5th of September, and the topic will be beam lengths. And actually, we made it perfectly on time. So this is all from my side today. Thank you very much for being here with me, and I hope I'll see you another time. Thank you very much, and bye-bye.